Thank you. So I am Savvidou. I am a PhD student at the Max Planck Institute for Astrophysics in Heidelberg, and I'm working in the group of Bertram Bits. And today I will be talking about the growth of super-Earths and specifically via pebble accretion and how important it is to have self-consistent disk structures. So as we've seen in the previous talks, in the recent years, we've had a lot of observations of exoplanets, which makes things very interesting, of course. And we can see that we can already see in a diagram like that, when we have the mass of the planets and their orbits, we can see that we may recognize distinct, let's say, populations of exoplanets. And one of them, actually one of the most abundant that we can observe right now, is the super-Earths. And this is one of the reasons why we'll be focusing on them today. Another reason is because in the recent years, there have been some studies suggesting a peas in a pod scheme. And that means that planets in super-Earth systems have been found to have similar sizes and also similar masses when they form within the same planetary system. This has also been supported by more recent studies now. And also another interesting factor for the super-Earths is that we do not find one in our solar system. So we want to understand them and more specifically study how they form. So I will be talking today about our model, which includes the viscous disk evolution and the stellar radiation. It's based on our previous work, also with the same code from a previous paper in 2020. And we follow the alpha prescription for viscosity. And this will be an important parameter that I will talk about in the next slides, because it points to the strength of the disk turbulence. So it's one of the important factors that determine the structure of the disk. And in this model, we also include the dust growth. And for the dust growth, in this work, we just have an MRN grain size distribution, but instead of a fixed maximum size, we instead have it limited by the fragmentation barrier. So this is disk dependent. And we also have the detailed opacities for its grain size, which were also included in our previous work. Then we include the pebble accretion following the Lambert and Johansen 2014 prescription. And to briefly introduce you to pebble accretion, what we mean by that is that we can have the protoplanet, for example, here. And then when you have planetesimals, which in the classical co-accretion scenario, we're supposed to collide with each other and form bigger objects. These planetesimals basically will kind of scatter around the protoplanet when it becomes massive enough and actually miss it. So we kind of become limited and the growth timescales become very large in order to grow planets this way. So instead, we can have pebbles, which are smaller objects around millimeter to centimeter sizes, which form after the grain growth of the dust, of course. And then these objects will basically get attracted by the protoplanet and get accreted to form larger cores, for example, or the planet itself. So in this model, we use planetary seeds of around moon masses, and those grow until the pebble isolation mass, which is basically the mass at which point the planet has accreted enough material to carve a gap in the protoplanetary disk. And this creates a pressure pump that basically forces all the dust exterior to the planet to be stopped, to be trapped there and not be accreted by the planet anymore. So this means that it's basically a self-terminating mechanism for the growth of a planet. We also include the pebble evaporation at the ice lines, and we include all the major ice and rock forming species. You can see here basically how we lose some of the material. This is the dust to gas ratio. So basically we lose some of the material each time we move across an ice line and we lose one element. And yeah, I also wanted to mention for the pebble isolation mass that it is strongly dependent on the local disk parameters. For example, the aspect ratio that I will talk about later, and the alpha viscosity. These are the major ones that it is dependent on. So it is important to have a model and to check what happens with the disk structure for those specific parameters and see how then the growth of the super-Earths will be affected. So I will start here now already with the results. And we have tested, we have run several different models where we test different alpha values. Alpha is this viscosity parameter that I talked previously. So we test three different values for the alpha. And then we also test two different fragmentation velocities. And these velocities are basically the maximum velocity that two dust particles can have, or two pebbles to make it easier, can have before they fragment when they collide instead of creating something bigger. So we have two different parameters that we're testing. I'm plotting here the, I'm sorry, I think the y-axis is missing. It's just the orbital distance. So it's r in AU. And on the y-axis is the h/r, which is the aspect ratio, so the height of the disk over its radius. And the different colors, I'm sure it should also have been showing the legend, but it will be in the next slide. So the colors here are different surface densities. And the reason why we choose, for example, these four is to have an estimate, kind of an indication of the age of the disk, which is not easy to do just by the surface density, but very crudely speaking, a younger disk will tend to have higher surface density, and as the disk evolves in time, then the surface density will decrease. So we can kind of approximate what will happen as the disk evolves. And then those blue lines here are basically the ice lines that I talked before. So where the species that we include in the model basically evaporate. And the most important one is this one here, which is the water ice line. And we can see that this is the one that affects the disk structure the most. We sometimes have some perturbations because of the evaporation of the other species that create a bump in the disk and kind of shadow the region afterwards. And then because of convection, we have this kind of small instabilities, which is not necessarily stability, these small, like, let's say, perturbations in the disk. But the important thing here, what we can already see is that the aspect ratios are basically almost flat for all of the different models that we have here. And this has important implications in the peas in a pod scheme that I showed earlier, because as I will show you in the next slide, the pebble isolation masses are a direct link to this aspect ratio. And when we have these flat profiles in the aspect ratio, it means basically that the pebble isolation masses, so the maximum mass that the planets can reach, will also be kind of similar within the same disk, so within the same planetary system. Also, we can see that for different fragmentation velocities, so when we increase the fragmentation velocity, basically the disks become colder and the aspect ratio is lower since they're connected by the thermodynamical equilibrium. And this happens because with the larger fragmentation velocities, this means that we basically can have larger particles, and the larger particles have larger opacities, which lower opacities, which means that the disk can cool furthermore, it can cool more easily. And also another thing is that we have almost the same, like very similar aspect ratios, similar disk profiles. And this happens because at some point the disk is so cool that we don't have the viscous heating anymore mattering that much. So this alpha parameter, but the stellar radiation, which would be the same for all of the different disks. And in the same way, that's what we also see for this alpha parameter, that the larger it is, the more important the viscous heating is, of course, and the more hot and high the aspect ratio is. So moving on here, we can now see the pebble isolation masses. So these are basically a tracker for us of the maximum mass that the planet can reach. It's for the same models that I showed before. And we can see again, first of all, what I said, that the profiles here are flat, which means if we had planets growing in that same disk, then they would have similar masses. And the Milholland research suggests that also that would mean similar sizes. And we can see that these different parameters affect the maximum mass that we can reach. So the higher the alpha is, the higher the maximum mass that we can have in the disk. And we have overplotted here the planets, which can be derived by the Kepler mission by a mass radius relationship. We can derive the masses and overplot them here to compare. And we also have some planets detected by RV. And the goal was to see how our models compare basically with these observed populations that we have, if we can basically explain them and conclude that a super Earth must have formed via pebble accretion. But as we can see, it becomes kind of difficult, especially for very low alpha or for large fragmentation velocities, because our maximum masses are much lower than the observed populations. So just looking at this, we would conclude that higher alpha is the one needed, especially like in both cases, in order to explain this. But then this is not the only thing that we should consider. We should also consider, that's just the conclusion that basically high alpha is what we want and high fragmentation velocities. This is not the only thing that we should think about. We should also consider how long it takes basically for these planets to grow, because in the first case, for the high alpha here and the low fragmentation velocity that we had seen some pretty massive planets being able to be formed, it actually would take them too long. And in this gray band here, I have put like the typical lifetime of a disk, like 3 to 10 million years. So the time it would take for the disk to be, for the gas of the disk to be dispersed. We can see that basically takes too long, and in most of the different surface densities, basically the planets would not have reached this maximum mass by that time. And in the scenarios where basically we have enough time to reach this maximum mass, as we've seen previously, the masses are not enough to explain the observed populations. So basically we have to think, okay, what about other initial parameters? Since we see it's so dependent and so sensitive to those parameters, what if we kind of tweak what we chose in the beginning to see how it goes if it improves the picture? And we have tested higher gas-to-gas ratios. Our nominal value was 1.5%. So we also checked 2 and 3%. And we basically find, as expected, that the maximum masses we can reach are, of course, a bit higher since we have more solids that can be accreted onto the planet. But at the same time, the difference is not that big, especially for just the 2%. We would need double the amount of solids to reach something like from 5 Earth masses to reach, like, let's say 7 or 8. So then we also tested higher gas surface densities, which would imply, as I said, very crudely, earlier stages of the disk evolution, so younger disks. And there we can see a much better improvement, and we can see that we reach more than 11 Earth masses, especially in the outer disk. But at the same time, we can wonder whether these high disk masses would be actually something so popular as we find, like, for example, for the to compare with the super Earths we observe right now. And then when we check the time it takes, of course, everything again is within a reasonable time scale below the lifetime of the disk, but at the same time, it is not significantly improved. So we have also then tested higher initial masses for the planetary seeds. So our nominal value was moon masses, and then we increased, we have 10 times heavier initial planetary seeds to check how that compares. And then we find that the time scale, of course, becomes a little bit better, but still it's kind of worrying and not within the safe limits for the lifetime of a disk.
Yeah, 2 minutes or less.
Yes, thank you. So we would conclude that based on the model, the models that we have run, the best set of parameters would be for an alpha of 10 to the minus 3 and a fragmentation velocity of 10 meters per second. So the higher velocities. As I've shown in these two plots, and there's another easier way to see it here in this plot where I have the masses of the planets and the time it takes for them to form. And these are the different models that I've shown. And this is for the specific parameters. We can see we have the higher masses, and it takes a relatively short amount of time to build them. which would mean that we are safe to assume that it would be possible. And a general conclusion would be that we would need any alpha value, any viscosity lower than 10 to the minus 4, and basically even high fragmentation velocity, or any alpha lower than 10 to the minus 3 if we have the high fragmentation velocity and the decreased collisions. And there has been recent research that also finds the same thing, that alpha needs to be lower than 10 to the minus 4 in order to reach the pebble isolation mass in time. And they also find the maximum masses to be around 7 Earth masses for alpha equal to 10 to the minus 5. And that means that we're still kind of missing the higher end of this plot here. And I can already go to the conclusions to discuss about it. So basically, our conclusions are that, first of all, the resulting aspect ratios are almost constant with orbital distance. That means we have constant pebble isolation masses in the radial direction, and this supports the suggested very recent studies peas in a pod constraint, where basically super Earths in the same planetary system have similar masses and similar radii. We find a trade-off between the pebble isolation mass and the growth timescale. And the masses of the majority of the observed super Earths can probably not be explained by pebble accretion only, but we could instead have some collisions after the gas dispersal, or we need some dust traps, for example, some traffic jams in the condensation lines, the evaporation fronts that I talked about, or some pressure pumps because of the planets that have already formed. And the conditions in the protoplanetary disks are shown to be very determinant for the various planet formation mechanisms, because there are specific parameters, for example, the viscosity or the fragmentation velocities that matter too much for the disk structure and then subsequently for the planet formation. So it is important when we consider such models to have a self-consistent treatment, because if we don't, then sometimes we can be we can overestimate, basically, for example, the maximum masses that we can have. And yeah, that's it. So thank you very much.